Now we're going to get some practice finding domain of rational functions, and then deciding if we have a vertical asymptote or a hole at the canceled factor. First, we will start by finding the domain of this rational function. To find the domain of the function, we will take the denominator, set it equal to 0, solve for x. So it's already factored for us. We will set each of those factors equal to 0. X equals 0 is one of our values, and solving this for x, we get x equals -6. Both of these values will be excluded from the real number line. So that's something also that we want to keep in mind, is that this represents all the real numbers, so it's a real number line. And we are going to put our x values on the number line in order. So smaller numbers on the left, larger numbers on the right. And we're going to put open circles above those x values. So we're going to exclude those x values from the domain, and we're going to highlight or include every x value in between, to the right and to the left. So our domain will be from -infinity all the way to -6, not including -6, and then again from -6 to 0, and then again from 0 to infinity. That's a positive infinity. We'll put union symbols everywhere we have gaps on our number line, and this becomes the domain of our rational function. The second part of our question is, do we have a vertical asymptote or a hole at those two x value exclusions? So do we have a hole at x equals 0 or a vertical asymptote? And do we have a hole at x equals -6 or a vertical asymptote? So how do these exclusions manifest themselves on the graph? In order to decide, do we have a vertical asymptote or a hole, we will factor and cancel the original function as much as we can. When we look at that numerator, x plus 3, there's nothing we can do to factor that, and the denominator is already factored. And when we think back to how we cancel common factors, if we have a binomial and a binomial, those belong in the same category, but they only cancel if they are identical. Remember, this is a monomial factor, and so that's not going to cancel unless we have another monomial factor. So nothing cancels. If nothing cancels, then I'm left with x times x plus 6. Both factors stay. If factors stay, then we know that we have vertical asymptotes at the x values that factors stay in the denominator. So x is one of our factors that stays in the denominator. We will have a vertical asymptote at what makes that factor equal 0. X plus 6 also stayed in the denominator and did not cancel out. So we will have a vertical asymptote at what makes that factor equal 0. So in this case, we have two vertical asymptotes for part A. For part B, we want to do the same thing. For part B, I would like to find the domain of the rational function. We want to find what x values are being excluded. So we will take our denominator, set it equal to 0, solve for x. We're going to solve by factoring using our zero product theorem. Set each one of those factors equal to 0. Solve for x. So we're using ZPT. Now we know we're going to exclude x equals 6 and x equals 7. So we are going to exclude x equals 6 and x equals 7 from the real number line. So we want to remind ourselves again that this represents all real numbers. So 6 and 7 will be excluded. We will put open circles above 6 and 7 on the number line to indicate that they are not included as part of the domain, but we will highlight the rest of the number line, and then we will give our domain as all the highlighted blue portions. So from negative infinity to 6, not including 6, union symbol, and then again from 6 to 7, and then we have a gap, so we will not include 7, but then we will include everything from 7 to infinity. So 6 and 7 are excluded from the number line, but the next question is, how are they excluded from the number line? Do we have a vertical asymptote, or do we have a hole at x equals 6 and x equals 7? To determine that, we are going to take the original fraction and we are going to factor the top and the bottom as much as possible. So the top doesn't factor, but the bottom will factor as x minus 6 and x minus 7, and we want to know if anything cancels. So in this case, x minus 7 is a binomial that has an identical binomial in the denominator, also of x minus 7. So our reduced fraction would be 1 over x minus 6. X minus 7 cancels. When we have a factor that cancels, we will have a hole at the canceled factor. So we will have a hole at the x value that causes that canceled factor to equal 0. So we have a hole at x equals 7. X minus 6 was a factor that stays in the denominator and does not cancel out. At factors that stay, we will have a vertical asymptote at whatever makes that factor equal 0. So in this case, since x minus 6 stays in the denominator of the fraction and does not cancel out, that is an indicator that x equals 6 will be a vertical asymptote on our graph. So in this case, we have one hole and we have one vertical asymptote. So we can also have combinations of holes and vertical asymptotes on our graph. For part C, we are going to start out again the same way. We are going to find the domain, and we're going to do that by taking the denominator of the rational function, setting it equal to 0, and solving for x. We get x equals negative 12. We will draw our real number line, put negative 12 on our real number line, put an open circle at negative 12, and then highlight the rest of the number line. So our domain will be all of the x values that we highlighted on the number line. So from negative infinity all the way to negative 12, and then again from negative 12 to positive infinity. Union symbol in between. So our next question is, do we have a hole or a vertical asymptote at x equals negative 12? To answer this question, we will factor the numerator and the denominator. In this case, the numerator will factor as x times x. What do we have? Opposite signs. We have a positive 12 and a negative 3. Our denominator will not be able to factor, so that's just x plus 12. And in this case, we notice that x plus 12 is a binomial that has an identical binomial of x plus 12 in our denominator. So this cancels. Anytime a factor cancels from the denominator, we know that we have a hole at the factor, at the x value that causes that factor to equal 0. So when we cancel, that gives us a hole in the graph. So canceled factors manifest themselves as holes in the graph. Okay, for our last example, we're asked to find the domain of the function and then determine if we have any x values that are excluded from the domain. Do we have a hole or a vertical asymptote there? So we're going to find the domain of the function. So in order to do that, we will take the denominator, set it equal to 0, solve for x. We have a quadratic term and a constant term. We do not have a linear term. So I'm going to use the square root method, and I'm going to subtract 21 from both sides. And then I'm going to take the square root of both sides. Square root, plus minus. So our x value turns out to be plus or minus, we have I times the square root of 21. Now we want to keep in mind that this is an imaginary exclusion for x. This is going to be interesting when we go to the next line, because step 3 says draw the real number line. Now remember that this is a real number line and there are no imaginary numbers to plot on a real number line. So we're not able to put this on the number line. Now remember, once we've done that, once we plotted that x value on the number line, in this case we cannot because it's imaginary, then we're asked to find the domain. In this case, since there's no x value to actually plot, the domain will be just from negative infinity all the way to positive infinity. So what we're saying here are there are no real number problems. So there are no x values that are real that will cause a problem for the function. So if you have imaginary problems for x, then you have no real number problems. In that case, your domain will be all real numbers. So the entire real number line from negative infinity to positive infinity. If there are no x value exclusions, then there can be no holes and no vertical asymptotes.